Good morning, everybody. Today, yesterday we discussed regarding the TLM principle and its concept, and also we discussed regarding we solved some two problems on that. Now today we'll start with another one or two problems we solve on TLM principle, and then we'll proceed with work energy method. Now take down a problem on this. So just I am trying to cover all varieties of problems, at least one, so that you will be able to understand the overall concept of the Lambert principle. Now we'll start with next problem. Take down a motorist traveling at a speed of 70 kilometers per hour. A motorist is traveling at a speed of 70 kilometers per hour. Suddenly applies brakes and halts after skidding 50 meters. Suddenly applies brakes and halts after skidding 50 meter distance. Determine the time required to stop the car. Determine the time required to stop the car and also the coefficient of friction between tires and the road surface. The coefficient of friction between the tire and road surface. Now first of all, as you know that the vehicle is moving, weight of the vehicle is not given. Take weight of the vehicle as weight of the vehicle is W Newton, and the velocity of the vehicle is 70 kilometers per hour. The velocity of the vehicle given is 70 kilometers per hour, and the distance it travels is S is equal to 50 meters. Okay. So, if this is a road pavement, road surface, on that the vehicle is moving with certain velocity and suddenly applies brakes. After applying brakes, the vehicle travels distance from A to B. A is the place where you are applying brakes, B where it halts. So, this distance is S, that is 50 meters. The initial velocity of the vehicle at this point is U, and that is equal to 70 kilometers per hour when it is moving at that speed, and suddenly brake is applied, and the final velocity is 0 kilometers per hour. Then we will convert it into meters per second velocity, but this is the velocity finally you will get it. So within 50 meters span, it is able to stop it. Now first of all, we can apply the Lambert's principle and we will work out. First of all, you apply kinematic linear equations to work out T and the acceleration, and then we will work out coefficient of friction between the tires and the road surface. So first of all, you convert that initial velocity V and initial velocity is, I think this is U and this is V, because this is V, U, that is correct, 70 kilometers per hour. This is, I will take it as initial velocity U, and the initial velocity is U is equal to 70 kilometers per hour, and you convert it into meters per second. 70 into 1000 meters per second, you work out multiple per hour it is there, and it works out roughly 19.44 meters per second. The initial velocity of the car works out 19.44 meters per second. I converted just into meters per second. And this is the initial velocity and this is the final velocity. This is V. V is equal to 0 meters per second. V is equal to 0 meters per second. You apply the kinematic equation for this one. V is equal to U plus, I can take V square minus U square is equal to 2AS. There are three equations. Out of that, one you apply. I know V, I know U, and I know S. So I can work out the A, acceleration. From this equation, substitute the values. V is equal to 0 square, final velocity. Initial velocity is 19.44 meters per second is equal to 2. I don't know what is the acceleration, and I know how much distance it takes to stop, that is 50 meters. So you will get A, that is acceleration of the acceleration, but actually if it is increasing the velocity, then I call it as acceleration. Here it will goes on decreases to 0, therefore instead of acceleration I call it as retardation. We call it as retardation, and that is equal to A. It works out roughly 3.78 meters per second square. 3.78 meters per second square. With that retardation, the vehicle will stop at 0. Now I got this one. I need to work out how much time it requires. That also they asked. To work out the T, I use the equation V is equal to U plus AT. The second equation. This is one equation now I use, linear. First I have given you in the first yesterday's class. All these three equations. You might have already done it in your PhD level. Anyway, we'll use this equation. Now in this equation, I know A, I know U, I know V. I only unknown T. Just substitute the parameters. V is equal to 0, U is equal to 19.44, plus A is equal to 3.78. Retardation, I will take it as minus, into T. From this equation, you will get T is equal to 5.14 seconds. You work out, calculate it and see it, whether it might, by chance any mistakes are there, just you inform me again. So that most of the things are correct. It is 5.14 seconds. That is the time required to stop the vehicle. So these are the parameters I have worked out. Now I want to work out what is the coefficient of friction between the tire and wheel. Now for that, just what I will do, I will apply the basic things of D element principle. That is the weight of the vehicle, I will take it as W because that is not given, W Newton. And there is a equal and opposite reaction, and that is N. And as the vehicle is applied brakes, there is a friction between tire and the pavements. So therefore, this friction will always act opposite to that. I will take it as F. That is acting opposite to the direction of the movement. If vehicle is moving this way, it will be acting opposite to that. The friction is taken as F, and I'll show it some different colors here. This is F. I think you can clearly see this one. F, and these are the forces will act. In addition to that, there is an inertia force is also acting. So when inertia force will be always opposite to the direction of the acceleration. If the vehicle is accelerating, increasing the speed, the inertia force will be acting opposite to that. If the vehicle velocity acceleration goes on decreasing, that is retardation, then it will be acting opposite to that one. As in this case, the acceleration is in this direction, the acceleration will be in this direction because it goes on decreases. So therefore, there is inertia force, I call it as MA, is acting in this direction. That is a little bit confusing factor because any other cases you consider, that point will be confusing. So inertia force in which direction it acts, always normally most of the times opposite to the direction of the movement, that is one thing. But in this case what happens, the vehicle is moving in this direction, but I am taking the inertia force also in the same direction. There is a confusing point. The reason is that here the acceleration decreases. So therefore inertia force will be opposing that. So therefore inertia, if you are applying brakes, your vehicle will try to stop, but inertia force is pushing that one. That is what inertia force is acting in this direction. So therefore this will be equal to W by G into A, acceleration into get. So these are the forces the acting, and the vehicle is under dynamic equilibrium after application of the brakes. So based on this, I have to work out what are the coefficient of friction between this one. Now first of all, I need to know what is N. N you can directly equate, there is no weight is acting downwards, the reaction is upwards, N is equal to W. And if you want to calculate F, F is equal to mu into N. So therefore is equal to mu into W. Newton. I am taking unit Newton as weight is also I consider in Newton. So the frictional force of mu into W is acting opposite to that. Now I will apply dynamic equilibrium in the horizontal direction for this one. Dynamic equilibrium in horizontal direction on the car. If you apply this one, just equate it to 0. F is acting in this direction, I will take minus, and inertia force is acting in this direction, I will take it as plus. So I will take it as Ma is W by G into A minus F. Any other things, any other force is acting? Inertia force and frictional force. Those two are the only two which will balance it. Is equal to 0. Therefore, A W by G into A. F is equal to, I know it. A is acceleration due to gravity. That we have worked out that acceleration 3.78 meters per second. That is acting in this direction, already I have taken it, meters per second. Minus F is frictional force mu W 0. Just equate it. The only unknown W cancels, take out common from this one, and the only unknown is mu. And G is equal to, you take 9.81 meters per second, and substitute that and solve it for mu. You will get mu is equal to around 0.385. You will get mu is equal to 0.385. That is the coefficient of friction between tire and the road pavement surface. Okay. Now we will go for the next problem, one more problem on the D'Alembert's principles. So here in this case we will take interconnected bodies, and one more problem on strings and pulleys. Those two problems will with that we will conclude this part. We take down this problem, second problem. Two weights, 800 Newton and 200 Newton. Two weights, 800 Newton and 200 Newton are connected by a thread. And they move along a rough horizontal plane. Under the action of force 400 Newton applied to the 800 Newton weight, as I will show it on the board. Okay. The coefficient of friction between the sliding surface of the weights, the coefficient of friction between the sliding surfaces of the weights and the plane is 0.3. Using D'Alembert's principle, determine the acceleration of the weight and tension in the thread. Determine the acceleration of the weight and tension in the thread. acceleration of the weight, and I think beyond this I may not proceed. Now I'll show the figure here. That is a road surface. On that there is one block is here and other block is here, and on that surface there are two blocks and they are connected by a string, okay, and it is pulled in this direction by 400 Newton force P. 400 Newton force is applied. Weight of this block is 200 Newton. I call it as the block A, and this block is having 800 Newton. I call it this as block B. Okay. This is the, and coefficient of friction between these two is mu is equal to 0.3. That is what they have mentioned. There are two things they have asked you to determine. One is acceleration and other is tension in the thread. We have to determine tension in the thread as well as acceleration of those two blocks. Those two things are required. Now we will go by the basics of the elements principle. That first of all you show the free body diagram of both the blocks. Now the way it is acting, there is a normal reaction N1, and as it is pulled in this right direction, therefore both the blocks will move. The direction of the movement is in this. It moves in this direction. Okay. So as both the blocks are moving in this direction, our frictional force will be acting in this direction. I call it as F1, and N1 is the reaction, and this is for this block. There is a reaction vertical N2 and the frictional force F2 acting opposite to the direction of the movement. Always the frictional force will act opposite to the direction of the movement. Now these are the two forces are acting, and the loads, all the things are shown except the string, that is what you have provided here, is under tension because it is pulling here. This is pulling this side, therefore this block will pull this one. So there is a tension in this one. The direction of the tension, how you take, always will be taken like this for this block, and it will be taken like this for this block. Okay. That I already explained you while solving string problems in equilibrium conditions, suspended weights. So how the direction should be taken in tension? Why you should take like this? Compression will be opposite to that. So therefore, now there are one more thing is there. Here, as these two blocks will be under dynamic equilibrium as per the elements principle, therefore the inertia forces will oppose the direction of the movement, and they will be acting opposite to the direction of the movement because the acceleration will increase in this direction. So don't confuse with that. Earlier problem was retardation. So and here the inertia forces will be acting opposite to that. This is one MA, and this is second. For this also it is MA like this. Now M is W by G. I can write it as W is the weight, that is 200 Newton by G into A. For this one it is 800 by G into A. Acceleration A. We need to calculate acceleration. And the tension between those two is T, and it is applied and pulled by a force of 400 Newton. Now each block, first of all you work out F1 and F2, and then for the free body diagram of each block A and block B separately, you write down the dynamic equilibrium equation, and there will be two equations. Solve the two equations, you will get the two unknowns. Now in this case, N1 is equal to, I will write here only, 200 Newton as it is direct straight brick, and F1 is equal to mu N1. Mu is 0.3. I will write here 0.3 into N1 is 200. Okay. This will get, I think, 60 Newton. Okay. Now similarly for this one, N2 is equal to 800 Newton and F2 is equal to 0.3 into 800 Newton is 240 Newton, I think. Calculation you can see, you will get around 240 Newton, correct. So the frictional force for both I have worked out separately. Now I will consider the block A. Consider block A dynamic equilibrium in horizontal direction. I have written in short form in horizontal direction. So for this one you applied dynamic equilibrium. MA is acting in this direction, F1 is acting in this direction, tension is acting in this direction. So T, I will take it positive, okay, is T minus F1. F1 is 60 Newton minus W 200 by G, 200 by G into A is equal to 0. 200 by G into A, that is equal to 0. That is, there are only three forces will be acting, and this I call it as equation 1. Same, consider block B, okay. So here also apply dynamic equilibrium. It is subjected to T in this direction, there is a force P acting in this direction, and just now I took T as positive on that side. Now here I will take P as positive. So therefore in the right direction of x-axis will be always positive 400. So minus T. Now we have to consider only this direction will be opposite to that. And it is pulling that one. And minus T. And F2 is also acting in this direction. Minus F2 is 240 Newton. And inertia force 800 by G into A, that is also acting opposite to that, minus 800 upon G into A is equal to 0. This is the second equation you will get from this one. For block B I got one equation, for block A I got one equation under dynamic equilibrium in the horizontal direction. If you can solve, either equate both the equation right in terms of T is equal to this, also T is equal to, and just equate it. And you solve, there are two equations and two unknowns. So therefore, you will get acceleration and T by solving these two equations. You can solve that one by simultaneous equations, those two are, and you will get actually 0.981 meters per second square acceleration. Acceleration 0.981 meters per second square, and this second is T, tension in the string. Both the thing you will get one value, you will get A, substitute that value of A in any one of the equation, you will get T. The tension in the string is 80 Newton. The tension in the string is, so all the problems are related to that. Same in this way you can solve by applying G. Lambert's principle. Now we will go for on topic that will be slightly different than this. Just to subject. Okay. Okay. Now we'll go for the next is that take down the problem. I'll remove this problem first. Take another problem. Determine the tension in the string. Determine the tension in the string. Determine the tension in the. I'll take the problem. Determine the tension in the string and accelerations of block A and B. Determine the tension in the string and accelerations of block A and B weighing 1500 Newton and 500 Newton. Weighing 1500 Newton and 500 Newton. Connected by an inextensible string as shown in the figure. Assume pulleys as frictionless and weightless. Assume pulleys as frictionless and weightless. Assume the pulleys as frictionless and weightless. Okay. This is a problem. Just I'll show you the figure, then you'll come to know the correct idea of this one. That is, it is suspended all these things to the roof of a floor. There two pulleys are suspended. One is here. This is one pulley, and the string passes through that, and there is one more pulley. Okay, and from that the weight is suspended. This weight is 500 Newton. I think I'll show it outside. Newton weight is acting here. Now, this is weight of around 1500 as they are given in the problem, is suspended to the block. This I call it as pulley A, and this I call it as, this pulley is connected to the top floor as B, and these are the string is continuous. This string is continuous, passes through that, it passes through that, and suspended here. Okay. This is the arrangement. If you leave this one, it starts moving downward. Weight is less. If you leave this entire system, this weight is more. It starts moving downwards. That time what happens? It moves downwards, and this weight will be lifted up in the upward direction. That is what is going to happen. So with this reference to what they have asked you is that T and acceleration of block A, acceleration of block B. These are the three things they have asked you to determine. Tension in the string, it will be uniform throughout, and acceleration of block A is different, acceleration of block pulley A is different, acceleration of this block is different, acceleration of this block is different. The reason is that the arrangement of the pulley that they have made here. Now you can just apply your logic. Now if you leave it, what happens? It starts moving up. Okay. Now when it moves down, it has got the rope all round. So this, if it moves by a distance x, this will move by a distance double of that. Because this is only one string has to move. So here the half string will be taken here, half string will be wounded this side. So therefore, the velocity of this one and the movement velocity will be velocity of this one is double of this one, and acceleration also automatically double. So in this case, what you have to do is that first of all, the acceleration will be double as the velocity is also double. Now we can say that acceleration of this block is, I call it as A, and this block I call it as 2A. Acceleration of this block will be 2A as because of the alignment. Now simply you apply all the forces is shown as per Derivation principle. Now you can show it as 1500 Newton is acting downwards here. Don't take double. This I'll remove here inside. Just as I told the way the problem has given. 500 Newton is also acting downwards because of the weight of the block. There will be tension in the string, and tension will remain same. This is also tension. This is also tension in the string, and this block moves up, this block moves down. I'll show the direction of movement like this. This will be moving up. So always inertia force will be opposite to the direction of movement or direction of acceleration, whichever. So therefore, it is moving in the upward direction. The inertia force will be acting in the downward direction. MA. M is 500 Newton by G into A. A is equal to here 2A. A is equal to 2A. And in this direction, as the block is moving downwards, the inertia force will be acting in the opposite direction, MA. So that is equal to 1500 Newton by G into A, acceleration. Okay, these are the one thing. And forces acting, here will be 2T, here will be T. So these are the two, block A and block B. You can have for independent forces, you can take it on block. This as A, this as B, fully as well as block. Now I'll show you free body diagram of A. So therefore, consider free body diagram of A and apply dynamic equilibrium. Dynamic equilibrium in the vertical direction. Vertical direction. In the vertical direction I am applying. So now in this case for the block A, you can see here the weight is acting downwards, the tension is acting upwards. There are two strings, there will be 2T upwards minus 1500 weight is acting downwards. These two. In addition to that, inertia force is acting upwards. So therefore, I'll take it as plus 1500 by G into A is equal to 0. This is one equation. There are two unknowns. I got one equation for the block 1. And your free body diagram of block B and of block B, the inertia, you apply the dynamic equilibrium in the vertical direction. Okay, the 500 Newton is acting downwards, T is acting upwards. So I'll take T positive minus 500 Newton. And inertia force is acting in the upward direction. There is one confusion, let me tell you. Inertia force is acting downward. This curve, not this one. This is for this. Okay. Inertia force is acting downwards. So therefore, that is along with this, it will come 500 upon G. But the acceleration of this will be twice of that. So therefore, into 2A. This is equation number 2. Equation number 1 and equation number 2. There are two equations, two unknown. Solve these two. You will get acceleration is equal to, from solving this one, you will get 1.401 meters per second square is the acceleration A, and T is equal to tension in the string 642.89 Newton. 642.89 Newton. This is how these problems on the DL numbers are required to be covered. Okay. Now we'll start with next unit, method. We'll start with that one, and we'll start with work energy method, next topic in the dynamics only. As still 15 minutes time is there, we'll try to cover the theory aspect of that one, so that in the next session I will be able to attend problems on that. Okay, no problem. Work energy method. In this work energy method, there are three terms. One is work. What is work and other things. Second is energy, and third is power. These three are there. We need to have the clear idea about these three, and then we'll derive an equation for work energy equation, and using that equation we will be able to solve most of the problems associated with some. One thing is that in case of DL principle can also be used to solve these problems, but if they are related with acceleration, if you want to determine the acceleration and other things, distance and other things, then we can go for Derivation principle, that our problems will be very easily solved. If they are associated with velocity and time and other things, then better you should go for work energy method, work energy equation, you can use it, so that the work can be very easily solved this one. Now in this case, the concept is that the change of kinetic energies, any work you carry out from one stage to other stage, when a force is acting on an object, then there will be some change of movement of the object and other things. So there will be change of energies from one level to the other level, other position. So the difference of those energies will be taken, and from that you will be able to solve the unknown parameters. That is what you are doing. Now first of all, you should know what is work. That is, the work is nothing but the work is work done, that is force into distance. Suppose an object is there at some place, you are applying certain force on that, and that object moves to some other place. So what is the work? You are applying some force on that object and it moves certain distance. That is the work done by that object. So what is you want to quantify that one by this one, that is force into the distance. How much work is done? That will be force into the distance. That is called as the work done, and that can be nothing but the product of the force into the distance moved in the direction of that one. That is called as the work done. So therefore, the unit for this one is that whatever the work done you are writing here is force into the distance you have written. So that unit of the force F may be Newton and the unit of the distance D may be meter, and for this unit will be Newton meter. For that the unit will be Newton meter, and that unit is called joule. This is called 1 joule. Whatever the amount of work done, that will be expressed in terms of joule, that is equal to Newton meter. Suppose if you have kilonewton and meter, then we call it as kilojoule, K joule. And if it is in Newton millimeters, then it can be expressed as millijoule. Millijoule. Depends on the units you adopt for the work as well as for the distance it travels. The different joules will come across for this one. This is called work done. Work done is the force into the distance. Now next is that energy. Now energy is the stored maybe, or it may be kinetic energy. So therefore the energy is nothing but a capacity to do work. Capacity to do work. Energy is anything may have in different fields also you have different type of storage of energies. So in general you can take it as this energy can be, there will be basically classified into two. One is that potential energy, and second is that kinetic energy. Potential energy and the kinetic energy. Potential energy is due to the position. It is due to the position of the object. If we have stored some water in the elevated water tank, so that is a stored energy, a potential energy. Because from the lower levels, at any point, you can bring that water to that point. If the water is at lower level, if you want to lift it, you have to apply external energy. So therefore, this is called a potential energy. So therefore, if work done in case of potential energy is equal to W into H. H is the height of the storage you have done, and W is the weight of that one. So therefore, W into H, that much amount of energy is stored, and that is called as the potential energy. That is due to the position, capacity to do work, and this is big because of the position of the energy you have stored. Because of its altitude, you have some energy. And second is that kinetic energy. Because of the activities, there will be some kinetic energy will be there. So therefore, this kinetic energy can be worked out from this equation by with a certain example, but I will write directly the equations for this one, that show that equation directly. Is 1 by 2 into W by G V square. This is the equation for kinetic energy. 1 by 2, you can have a small derivation is there, but I will not go through that, it is not required. So therefore, 1 by 2 into W by G is there. That is the kinetic energy of that one. So as I told you, any problem you need to solve, what is the kinetic energy in the initial stage, what is the kinetic energy after change of position, and difference of that two will help you to determine the different parameters. So therefore, this is called kinetic energy equation. This is a very standard equation, as you know that 1 by 2 W by G into V square, okay, W by G V square. Now there is one more important equation is there, work energy equation, that will do it. Before that, come to the portion of power. This power is nothing but rate of doing work. Rate of doing work. Some work, we may do it, same work, I can do it very fast, same work, I can do it slowly. The amount of work done will remain same, but the rate of doing work, which is mainly depends on time, how much time, in what short time you will do it. So therefore, the power is also one of the important factors. So therefore, this power, rate of doing work is expressed in terms of watts. It is normally expressed in terms of watts, okay. Watts, and this 1 watt is equal to 1 joule of work done. 1 joule of work done per second is called watt. 1 joule of work done per second is called watt. And regarding capacity of to do the work, this also is in Newton meter, and this also unit is joule here. Here in case of power, it will be expressed in terms of watts, and 1 metric HP is equal to 735.75 watts, or 1 British HP, we are using British HP here, for 745.8 watts. These are about some units for power, okay. Now this much is sufficient for this one, but we will go directly into the derivation of the work energy equation. That is very important, the derivation. Still 4 minutes time is there, we can able to complete that equation. And work energy equation. I'll come out of this one. That is one important equation. If you derive that one, you will be able to solve problems from the next class. Okay. Work energy equation. Now consider there is a block which is subjected to a system of forces F acting on this in all the directions. Okay. The next resultant will act in this X direction. It moves to some other position. Okay. From A to, this is F1, F2, F3, F4. So my resultant of that will be acting in this direction. It moves for a distance of certain distance S, and initial velocity U, and the final velocity is V. It moves a distance of S, the block A, to the new position, to the point B. Work energy equation. Now, during that, there is some change of kinetic energy will take place. So those points I will take into consideration here. Now in this equation, that at this point of this one, as per the D.Lambert's principle, that principal R is equal to MA, we know it. Okay, so R is the resultant force. Though the system of forces acting on that block A, the resultant will be acting in this direction. Component of that resultant will be acting in the X direction. I am considering the distance moved in the X direction only. So therefore, is taken as R resultant, and M is the mass of the body. A is the acceleration of the guy, acceleration of the object from here to here. Now in this case, R is equal to MA, where MA is W by G into A. R is the resultant force. I will multiply both sides by ds. You multiply both sides by ds. This is nothing but based on Newton's second law only, as the Alamut's principle is based on Newton's second law. Same thing is applied here also. So therefore, I multiply both sides by R into ds is equal to W by G A into ds. Now, instead of acceleration, I will substitute the parameter in terms of dv by ds. That is, as you know that v is equal to, just for your understanding, velocity v is equal to what? Whatever the distance travelled by t dt, ds upon t. That is meters per second you will get any distance you travel, and the acceleration is based on